Hello and welcome back to Calculus 1, section 3.3, Rules of Differentiation. New word, differentiation. What is differentiation? Differentiation is the process of obtaining the derivative function. So let's define that. I don't think I actually ever defined that and wrote it down, but let's go. So differentiation is the process of calculating or obtaining the derivative function. So when I say differentiate x squared, it means get the derivative for x squared. So say differentiate x squared means get the derivative of x squared. So that's the meaning of the title. The word in the title. Now we know that the process of differentiation changes the original function into the derivative function. What is the function doing, right? Function is changing input number into output number, right? So for functions, you have, let's say, number 3 come in, function works on it, and it spits out, let's say, number 8. So functions change numbers from one number to another number. Differentiation will change a function f of x coming in, and I'll put this weird symbol inside d divided by dx, and that spits out the derivative of f of x. So differentiation doesn't change numbers directly. It changes them indirectly, obviously, but differentiation changes functions. So you know that you have mathematical operations that you put in between numbers, and you combine the numbers and change numbers. Square root of 16 is 4. You change 16 into 4 because you use the square root. Differentiation is going to change your function x squared into a function 2x. We call these operators. So operations change numbers into different numbers, and operators change functions into different functions. So we are going to regard integrals and derivatives as mathematical operators. They are going to change the function. So the next part we need to talk about is notation. So when I write d dx of f of x, immediately over here, example, d dx of x squared, this means instruction to take the derivative. You all understand instructions, license and registration. It's clear, plain, and simple. Give me the license and registration. So when you see this over here, the d dx, that is the instruction which says take the derivative of the function in the bracket. And then you will say, okay, the derivative of x squared is 2x because we learned it. That's coming up now. So that's the notation. d dx is the instruction. Later on, I'm erasing this, later on the instruction is take the integral of x squared in respect to x. So instruction is d dx, which means take the derivative, or the squiggly line integral, take the integral of f of x. And those are the two operators which we study in Calculus 1, 2, and 3, differential equations, and so on. So it's just a notation, it's just an instruction. Now, in terms of notation, we have the derivative, which we denoted earlier as f prime of x, also denoted as as y prime, y with a dot on top, df dx, dy dx, capital D of x. These are all notations that mean the same thing. The derivative of the function in respect to x variable. Now, I have to contrast the two ways in which you can deal with derivatives. Pick your poison and use it, right? But do not mix them. So here we go. I'm going to use the word or and divide the space into two. On the left-hand side, I'm going to have f of x is equal to x squared, and you going f prime of x is 2x in the next line. So this is one of the ways in which you can deal with the derivative. And I mean, clearly, if you write equals 2x, that's going to be terribly wrong, because x squared is not equal to 2x. You cannot say function is equal to the derivative. You have to go to the next line and write f prime or y with a dot, or any one of those, right? So any one of these would work here. I don't care which one you use, right? Except the original Newton equation, Newton's notation is extremely rarely used now. I actually had a professor who used it 15 years ago, and I haven't seen it since in all of the other education I had. And that professor was engineer. So probably some of the older mechanical engineer professors might be using this. If you're mechanical engineering and you go to 4-year school, you might run into the original Newton notation for derivative. Other than that, chances are zero that you're going to see it anywhere. You are going to see these puppies 99% of the time. And in this class, 90% of the time, right there. So you get to write function on one line, the derivative of the next. There is only one way to write this in line, which is what I have above. The derivative of x squared is 2x. If you connect the language, right, the way you speak with the notation, it should be clear. Look, function is x squared, the derivative is 2x, right? It has to make sense from language perspective. Function is x squared, that's the first line. Next line, the derivative is 2x. Now, on the other side, you say the derivative of x squared is 2x. So if you need to write these things down to make sense of them, right? And as I said, anytime you put x squared equals 2x, or whatever derivative we do later, clearly it's going to be wrong, because you're saying function is equal to x squared, which is 2x, which makes no sense. So you have to separate these. So if you want to write them in two lines, you will use the left side. If you want to write everything in line, which is what I'm going to do most of the time, 90% of the time I'm using the right side, sometimes it's beneficial to use the left. it's okay. So that's that part. So we have notation and language and words covered completely. Differentiation is the process of figuring out the derivative of the function. And to differentiate a function means to find its derivative. Derivatives and integrals are mathematical operators which change function from one function to another. Notation is take the derivative of f of x means instruction. Take the derivative. It's just an instruction. Like you have instruction 3 plus 8. You are supposed to add in comparison to 3 times 8, where you have to multiply. So it's just an instruction to take the derivative. And you have all different types of these, where the Newton and the Leibniz notation are the two that are used most of the time, where the Newton's notation evolved into these guys, which we use today, rather than placing, you know, dot and 2 dots for the second derivative and 3 dots for the third derivative. We just use these primes, 1 tick mark, 2 or 3 or so on. Leibniz notation, another mathematician who came up with the calculus and differentiation and everything at the same time when Newton did, and published it before Newton. Newton was really nasty character as a person. He was a nasty guy, really nasty person. He was brilliant in every aspect of his life in terms of research and physics and mathematics, but it was, you know, human garbage technically. To some degree, like Steve Jobs, like was able to do, but he was just a garbage person. So, yeah, read up. So Newton did his stuff and stuffed it in a desk because he said, yeah, I figured this out, right? It's mine, I can use it, you know, it's power, it's the top thing that the world had at the time. And he was able to understand all of the physics and so on. It was just all his. But then Leibniz comes up with the same thing and publishes it, and then Newton scrambles to publish his and says, hey, it's mine, I did it first, right? And then they had battle between them. For decades after that, they were going, you know, blood and knife on each other to get the credit for one of the most important inventions of our kind to date. So Leibniz notation is much better than Newton's notation, but again, and Leibniz is the guy who went full on economics and business and those types of applications, where Newton went physics and engineering and that stuff. So they really complemented and covered those first most important parts of application, right? The economics and business side, and also obviously physics and engineering side. So now we come to the point where we are supposed to learn rules of differentiation. Before I give you any of the rules, I have to give you motivation for those rules. At one point in life, you memorize that the 3 times 5 is 15. Now, some of you were forced to memorize this, and others actually saw it as a really cool shortcut and did it because of that. If we didn't have this, right, your alternative to computing is 3, plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15. So it's one or the other. Now this one, you get to compute. This one, you get to memorize. So you invest a little bit of time to memorize these puppies here, multiplication tables from 1 to 10, right? 1 times 1 through 10 times 10. And then, you know, learn the ways in which you can manipulate that to multiply 132 times 57. The alternative is 132 plus 132 plus 132 plus 132 plus 132 plus 132, right? 57 times. So we have brains and we are lazy by nature. So you want to do the easier thing every time. So you invest some time into learning multiplication tables so that you can cut this calculation every time you have to do it, and you have to do it a lot. What's the way to compute your derivatives? The difference quotient. We go all the way right to the previous lecture, to the top, and we see the difference quotient. And you go one lecture before to see the difference quotient at work every time. Wouldn't it be nice to have a one-liner for this instead of going to this limit every time? Of course you would, right? So this is where you now make rational or irrational decision. I am going to give you a whole bunch of formulas which you can memorize and take derivatives like this. Or you can ignore those formulas and not memorize them and use limit every single time. And the choice is yours. I will tell you that in all of the years I gave this choice, which is I'm teaching Calculus 1 for almost 10 years every year, 3 or 4 times, I did not have a single student who picked to do limit. But then, you know what? You might be the first. So let's see. So what follows now is a bunch of formulas which you must sit down and memorize. We can prove them all through the limit. Obviously, you prove the formula to the limit because every mathematical formula theorem has to be proven. So we can prove all these formulas using the limit definition. Well, it's not the honors class, so I kind of skip over that. Once I give these formulas, you must sit and memorize them to be able to use them. And you can't memorize them partially. You can't memorize some and not memorize others because they work as a group, obviously, to cover all of the problems that you see. So here's the first one. Memorize this. The derivative of the constant is 0. And I put a box around this thing. I'm going to spell this one out, and then every other one will be read the same way. So the derivative of the constant is 0. So the derivative of 2 is 0. The derivative of negative 10 is 0. The derivative of pi is 0. The derivative of 3 squared minus, in parentheses, 5 plus 8, everything to the negative 2 is 0. I don't even care what it computes to, okay? Because I know that these are all numbers, and whatever these numbers happen to be at the end, I'm going to get some kind of number which is a constant whose derivative is 0. So there we go, right? So the first one you are memorizing, if you want to, is derivative is 0. Derivative of a constant is 0. Which also ties in the previous lecture, the flat line, 0 slope, and all of that kind of stuff. That's technically what it is. The next formula which you are memorizing is the derivative of x to the power n, x squared, x to the 5th, 1 over x cubed, or square root of x. They all fall into this category, right? Is n x to the n minus 1. Is this thing going? Good. So your polynomials are in here. Remember your x squared. Now you know it's 2x. You do not have to do the limit now, right? So let's take a look at the derivative of x squared first. Clearly, when you compare these two, n is equal to 2. Right? So drop 2, and then n2 minus 1. So plug in, n equals 2 in the whole formula. And what you get? Sorry, it's x. You get 2x. So the derivative of x squared is 2x. What is the derivative? You tell me. What is the derivative of x to the 7? 7x to the 6. Your n is 7. You drop that in front of your x. So whatever power you have, you drop in front of x, and then just subtract 1. So n is 7. 7x. 7 minus 1 is 6. Or the limit of x plus h to the 7, Pascal's triangle to the coefficients for expansion of x plus h to the 7, and then after 30 minutes you have your 7x to the 6th power. Also on this pile, what is the derivative of 1 over x to the 8th? Well, we have to rewrite it a little bit, right? So the formula applies. What should I just rewrite as?
X to the negative.
Thank you. X to the negative 8. Go on. Use the formula. What do we get?
Negative 8 x to the 9.
We get negative 8 x to the negative 9. Very good. Which is negative 8 over x to the 9. Perfect. You remember we computed this one? The derivative of 1 over x? We had it graphically. We had it done with the limit. We know what the answer is. What's the answer? Does anyone remember? Negative 1 over x squared. Good. But now, go ahead, rewrite it, unleash the formula upon it, and you will get the same answer. Go on. The first step is to rewrite this as x to the minus 1. Drop negative 1. X to the minus 1 is minus 2. And there is your solution. Oh, come on. How about the derivative of square root of x? What should I rewrite this as in terms of exponents? X to the 1/2. Good. Go on. Tell me the answer. Okay. It's not the form that we are going to use, but you did the proper mathematical thing. You rationalized the denominator. Right? So the reason why I'm going to actually keep, let me so 1/2 and then x to the negative 1/2, because 1/2 minus 1 is negative 1/2, and that makes this go in the denominator. So negative makes the x go in denominator, and 1/2 gives it a root. And now the reason why I am not rationalizing this is I don't know what the value of x is, right? It could be 4, and then I don't have to rationalize. It could be 5, and then I have to. So I'm not going to bother rationalizing answers in calculus, final answers to problems, because this is not a number that is definitive. So I don't know what value, right? Why do extra work you might not have to? Does it make sense? So if the answer is 1 square root of 5 and you leave it like this, yeah, -1. Because, yeah. But if you leave it this, like that, perfect. Because this x could be 5, but it also could be 4. And if it's 4, no need to rationalize. Square root of 4 is 2, 2 times 2 is 4, so 1/4. No harm done. So you do not have to rationalize answers which are functions that contain root x of any sort in denominator. However, if you have a final answer with 1 over 2 root 5, or 2 root whatever is not rootable, then you have to rationalize that. So there you go. The first 2 rules to memorize. Derivative of constant is 0, and then derivative x to some kind of exponent. Now, whether that exponent is the integer for your polynomials, or fraction for your roots of all kinds. What's a 1/3 exponent? Cube root. Exactly. So you should not have an issue with a problem that says, what is the derivative of the cube root of x to the 5? Because you immediately need to have that algebra in your head to rewrite this as x to the 5/3, and then just go, okay, drop 5/3, x to the -1, common denominator, 5 minus 3 is 2, so 2/3 over here. And you can leave it like that, or you can go 5/3 times the cube root of x squared. You know, whatever you prefer. But this is just fine. All right, that's that. So we have constants, and we have these with exponents. Now we have a little bit different rule. This rule contains gives us this rule gives us power, I should say, gives us opportunity or whatever to add and subtract derivatives. So the derivative of f of x plus or minus g of x, so if you either add them or subtract them, is the same if you took each derivative individually. We had this rule for limits. This allows you to deal with multiple terms, term-wise. So what is the derivative of x to the 6 plus x cubed minus 9? Now, clearly you will just write the answer within a week, but now we are learning, so I'm going to say this is the derivative of x to the 6 separately done, so plus the derivative of x cubed separately done minus the derivative of 9. So the rule allows us to work on individual terms separately. This does not work for multiplication, but it works for addition and subtraction. So what we have is 6x to the 5 plus 3x squared minus 0. So the answer is 6x to the 5th plus 3x squared. That's the answer. So we are allowed to work on these individually. Here's the example for you. So d dx of, again, you do not have to write this. You just need to understand that you are allowed to work on each one of these individually and just pile up the answers together. You do not have to write what I circled. It's just in your head. So what is the derivative of cube root of x minus 1 over x? So like the rules back to limit. I'll be back tomorrow. We are starting with two terms, we will end with two terms. What is the sign between the two terms in your answer? Positive. Good. It has to be positive, right? The problem has a negative, but when you take the derivative of 1 over x, you will get negative. So negative and negative is positive. Good. So I'm going to rewrite this first as the derivative of x to the 1/3 minus x to the negative 1. Then I will take the derivatives. Remember that when you are now using up this to change these, so don't put it again. I'm highly allergic when students in algebra do this. I said, you just used up the root to change 9 into 3. Don't put it up again. And that allergy goes through Calc1 again. I just hope that no one went limit of whatever the function is equal and then you wrote limit 3 or something like that, because that just boils my blood. You used up the limit to change this mess into a 3. There is no need to write the limit there, right? The answer is 3 and you're done. So the same thing goes here. You are going to use up this dx to change these two guys into new functions, so you are not going to put that d dx. And please connect that to your calculation. What's 3 plus 5? 8. Do you put plus anywhere when you're done? No, right? You used up that plus to combine these two into this, and that's it. So yeah, once you eat the banana, it's gone, all right? You can't eat it again. You can get a different one, but you can't eat the same one. Well, all right. back to the calculus problem where you can't do it again. So what do we have? We have the derivative of x to the 1. Yeah, welcome to my class. Sorry. But I'm actually not. Negative 2/3 minus negative 1 over x squared. We know these calculations from before. I am going to write this as 1 divided by 3 cube roots of x squared plus 1 over x squared. I don't have to go and add the common denominator and all that stuff. It's good. It's good enough. So this rule simply tells us if you have multiple terms to take the derivative of, take the derivative of each term independently of each other. Next rule. Another one of the rules.
Professor?
Yes.
For final answer, do you have to put the radical backwards? You keep it as 1 over 3 to the x.
You can keep this, yeah, sure. Please.
No. Further down. See how you put the radical?
Where? Further down. You mean to the side?
Further across. Yeah.
Haha, okay, good.
Further down the logic. 1 over 3, 3 root. Could you keep it as x to 2/3?
Yes.
Yeah.
You are allowed to write 2/3 over here, sure. It's going to be positive because it went in denominator. So the negative over here is what shifts it down, and then the exponent makes either the roots or you leave it as exponent. Yep. The next rule says that the derivative of constant times f of x, you can kick constant outside and focus only on the derivative of f of x. Oh, that's useful. What is the derivative of 9x squared? 18x. Done, right? And you will write 18x within a week. But right now, I'm going to say 9 can be kicked out of the calculation, and we are only focusing on taking the derivative of x squared, which is 9 times 2x, which is 18x. Now, it's obvious to everyone what's going to happen with you practicing this right down the line. You'll just go, oh yeah, 9 times 2 is 18. I expect you all to go from the statement of the problem to 18x directly. But you need to know the mechanics behind it. And the mechanics behind it say the derivative does not work with a 9. Right? If it was just 9, it would be 0. But it's a constant, right, coefficient that multiplies the function. So we can kick it outside and we can deal. You have the same rules for limits, right? You can kick the number outside, work on the function, and then just multiply by the number at the end. These two rules that I just had, the last two rules, are rules of linearity. And differential operator is a linear operator, so they have to apply. What is the derivative of 2 root x? Well, you already know that the derivative of root x is 1 over 2 root x. The 2's cancel, so you just have 1 over root x. So if you have something multiplying, you will simply just copy it and then multiply with it. There was... So one more rule, and that's it. Well, not lectured it, but rules it. And this rule says the derivative of e to the x is itself e to the x. And something they ask you to memorize for now, but it will be worked out later in this course. Derivative of e to the ax is a e to the ax. The upper one doesn't have an example because that is all of it, all right? But the one on the bottom, we can master the example. What is the derivative of e to the 5x? 5e to the 5x. Yeah. So please don't make it difficult. You replace a with a number everywhere, and that's it. The second line is part of something we call the chain rule. We learned that in 3.7-ish, I believe. 6, 7, something like that. So it's coming up next Saturday. So this formula is just for a short while for you to do the homework and some cute little examples before we get to the life-defining section. Should I say that? On chain rule? Yeah. Your mathematical education ends if you don't learn it. That's mildly to put it that way. Okay? That's the end of your road if you don't learn that chain rule. 99% of the you take after that lecture will be chain rule. And then integration kicks in. The most important integration technique is backwards chain rule, called U substitution. So yeah, you'll have to deal with that. Good. These are the rules. And the story goes, you memorize this stuff, you work out 5,000 examples, and that's it. So these two rules are like housekeeping rules, right? Of what to do when you have multiple terms and if you multiply your function with something, by something. And then you have the rules for polynomials, square roots, rational, and then constant, and then e. Trigonometry is going to have its own sections. There is going to be a section for trig functions and a section for inverse trig functions. And those are, I believe, 8 and 9 in this chapter. So the entire chapter 3 is concept first and then ways of taking derivatives. So in chapter 3. And then chapter 4 is application of derivatives, which means word problems, which means concepts, graphing functions by hand, and so on. So now we're learning the mechanics of it, and that's technically that's it. You can take higher order derivatives. Second derivative, third derivative, fourth derivative, fifth derivative. And some of those obviously have practical application. We are going to see very soon that you can regard a position function as the function. The first derivative of position function is going to be, does anyone know? Velocity function. And the second derivative of the position function will be acceleration function. Very good. And then the third derivative of the position function will be jerk, which is you experience jerk in your car every time when you slam your gas pedal or your brake. It jerks your body every time, right? So your gas pedal is accelerator. So that's actually acceleration, which is the second derivative of where you are in space. And the brake is deceleration, which is acceleration in the other direction. So it jerks you either into the steering wheel or into the seat, depending which one you press. Now, the jerk is the derivative of acceleration, so it measures the change of acceleration. If you slam on any of those, you experience a lot of jerk, right? Because you change the acceleration quickly. If you gradually push either one of them, you don't experience jerk at all because it was a gradual change, right? You see the derivatives work their way into these. We're going to have a whole lecture on what I just said. I believe 3.5 or 3.6. 3.6, I think. So it's coming up next week. So chapter 3, mechanics of taking derivatives. Now we are talking about higher derivatives. Higher order derivatives. So the order goes, function f of x is actually 0th derivative. It's the function. And then you have f prime, first derivative, f double prime, second derivative, f triple prime, third derivative, and then notation switches to a little number because it gets annoying with the tick marks. Then you have to go and really stare and count the tick marks. So notation changes into this one, and they can go as far as you want. I've never seen past the fourth derivative in application, but, you know, maybe you will figure something out as a researcher at one point that uses 16 derivatives, right? I don't know. So, original function, first derivative, second, third, fourth, fifth. Now, each of the derivatives is the first derivative of the previous derivative. So what's the second derivative? Second derivative is the first derivative of the first derivative. I'm going to write that down. So second derivative is the first derivative of the first derivative. And the fifth derivative is the first derivative of the fourth derivative. So in order to find the eighth derivative, you have to have all the 7 derivatives prior to that one. And there is no skipping them unless you know what's going to happen. Now, notation, you already seen the notation with the tick marks. We also have Leibniz notation for this, where the second derivative instruction looks like this. D squared over dx squared of, let's say, x cubed. Right? We all know what squares mean. Means 2 of those things, right? So I can rewrite this in Leibniz notation as this. And you see that you apply the first derivative, and then you apply another first derivative. But since you applied 2 first derivatives, you got the second derivative. Would this notation make sense with nesting like this? Do we all agree that this is a first derivative by our notation from before? And then you have to take another first derivative. But that's altogether 2 derivatives. So it's a second derivative as the answer. All right, let's take the first derivative. So copy the outside d dx. And what's the derivative of this thingy? 3x squared. Using our power formula, right, where n goes down, and then 3 minus 1 is 2. All right, cool. And now I have to take the first derivative of the first derivative, which is 6x. So you can write that the second derivative is 6x in this case. So all I did is I took the first derivative of the function, and then I added another derivative on top of that one to come up with the answer here. So this is the intermediate step, and guess what? You will always have to have the intermediate step and all of the intermediate steps. There is no skipping there. A practice for you. fellow comrades. d dx, square on each, second derivative obviously, of square root of x.
Figure those out.
But it's nice. It's nice to have a theory to the people would. I don't, so I don't know. Maria. All right. Second derivative. The first order of business is to find the first derivative of x to the 1/2, which we all know is, eventually will, which we all know is 1/2 root x. So I technically just broke it apart into dx times dx. So I wrote the second derivative as two first derivatives, nested, right?